Today, I'm going to talk about the combination of the hierarchical vortex clustering method with Liutex and its application to compressible transitional boundary layers and jets. My name is Kazuo Matsura from Matsuyama University, Japan. The original baseline method was developed together with Professor Emeritus Yasuhide Fukumoto of Kyushu University, and the work was published in Physical Review Fluids in 2022. The topic of this study is to decompose and categorize vortical regions into rational groups in order to understand vortex dynamics and the structures appearing in transitional boundary layers. First, I will explain the research background and our main objectives. Next, I will propose our hierarchical vortex clustering framework using data from a compressible boundary layer flow. In this framework, we look at clustering from different directional viewpoints. So I will talk about both the unidirectional and omnidirectional approaches. I will also introduce functional clustering, which focuses on grouping vertical points based on mathematical terms in governing equations. Then, using computational data from jet noise simulations, I will explain how we combine these clustering methods with Liutex to seek for more sophisticated clustering method. Finally, I will summarize my presentation. Laminar turbulent transition is a very complicated phenomenon. Here I'm showing DNS examples of natural transition and bypass transition. In natural transition of K regime, regular hairpin vortices are generated, and amalgamation of those hairpin vortices lead to turbulent boundary layers. On the other hand, in bypass transition, non-regular intermittent region of vortices are generated, and amalgamation of those regions lead to turbulent boundary layers. In industrial problems, the transition scenario is much more complicated. Here I'm showing an example of stator-rotor interaction in a gas turbine cascade. The wakes from upstream stator impinge on the blade boundary layers, and the generation and propagation of disturbances takes place inside blade boundary layers. In order to mechanically investigate the local dynamics appearing in transitional boundary layers, I previously proposed algorithmic exploration of the dominant local dynamics of hairpin vortices. In this method, I extract interior points of a vortex based on the ice surfaces of the second invariance of the velocity gradient tensor. Then I find nearly mean skeleton points, and after that I define the local neighborhood of a skeleton point. Then I decompose the right-hand side terms of the Navier-Stokes equations into non-further decomposable terms, large absolute value terms, and strong correlation terms. Then I could find reduced order representation of local dynamics for each skeleton point. This method is successful in mechanically investigating the local dynamics. However, we cannot track and investigate each vortex separately. So in this study, we develop a clustering method that can separate vortex clusters successfully and recognize them individually based on the physical connectivity among point clouds. The target flow for algorithmic construction is laminar turbulent transition of K regime under Mach number of 0.5. Here, I'm showing the introductory target image of the present vortex clustering. In the left figure, I'm plotting the distribution of omega x streamwise vorticity on the streamwise series of x-planes. Here, we observe the discrete and continuous large omega x regions. I want to extract these vertical regions separately and analyze these regions mechanically. We call Each group of vertical points superclusters and its mean curve skeleton. In order to achieve the goal, we introduce a brand new unified hierarchical cluster members named P cluster in this study. Here, P stands for proto, sub, super, or hyper. Proto cluster or point is a vertical point. A set of points close to each other on a plane is a cluster. We get a supercluster when we stack the planar clusters in a direction. We call the mean curve of the supercluster connecting the centers of gravity as a skeleton. We get hypercluster by accumulating superclusters in time. We get skeleton time surface by tracking skeleton in time. We also consider subsets of points as subclusters. Here, I explain the unidirectional clustering. In this method, first, we extract the points belonging to the large omega x on each jth plane. We call the mesh points constituting the clusters protoclusters or points. Here, in the framework of the unidirectional clustering method, using omega x is not necessarily needed for extracting vertical points. However, when we consider, for example, streamwise structure, omega x is a good sensor for the structure, so we use omega x here. Then we evaluate correlation between each cluster on two successive jth and j plus 1th planes in order to connect clusters in the direction. Sometimes we encounter multiple correspondence. In that case, in order to make that cluster structure simple, upstream cluster is divided into multiple clusters, each of which has one-to-one correspondence with downstream clusters. The division of the cluster on the jth plane introduces new multiple correspondence between the j minus 1th and the jth plane. So we iterate the backward division process through the whole domain and finally get single correspondences over the whole domain. Here I'm showing the results of the present unidirectional clustering. Here I'm showing the supercluster elements in skeletons. Superclusters and skeletons are successfully separated. Here, all skeletons of supercluster of strong vortices are shown. Skeletons with positive omega x are shown in red, and those with negative omega x are shown in blue. Here, I'm showing the distribution of omega x on the streamline series of x-planes and the skeletons of superclusters with omega x greater than some threshold. Because skeletons go through the original large omega x region, the present clustering is rational and successful. Here I'm showing the skeletons of near-wall vortices with omega x greater than some threshold. The pairing of the positive and negative skeletons are observed. I can actually construct skeleton time surfaces for this time period. The color shows the height from the wall. The previous unidirectional method is very effective when we focus on vortices with unidirectional structures. However, generally speaking, vortices are multiple oriented, so we extend the previous method to omnidirection. Two ways are considered. One is repeating x directional clustering in y and z directions. The other is clustering based on the vortex axis. Here, I talk about repeating the x-directional clustering algorithm in the y and z directions. I take up an example of clustering a vortex ring. When we extract vertical points by unidirectional component of vorticity greater than some threshold, original points are divided into two regions in each directional method. Superclusters and skeletons are generated correspondingly. By merging superclusters or skeletons of different directions, original vortex ring is reconstructed. Although at the level of skeletons, the boundary blur appear due to boundary effect. Reconstruction is exact at the level of superclusters. In the problem of helping vortices, legs and arches can be successfully reconstructed. Here, I talk about the results of clustering based on a vortex axis. Regarding the vortex ring, exact skeleton going through the center of the vortex ring is successfully constructed. Here, I explain the method to evaluate the center of gravity required for the construction of a skeleton. A point P is projected onto the plane going through the selected point P0 and having the normal vector n. Then neighboring points are similarly projected onto the plane, and the center of gravity is obtained by the average within the cluster. The present method is well applicable to the clustering of vortices in the late stage of transition as shown here. So far, we have considered clustering methods based on the connectivity by the Euclidean distance between points. We can also categorize points based on mathematical terms defined on those points. We call it functional clustering. By the functional clustering, we can categorize points based on local dynamics expressed by mathematical terms. Here, we take up a vorticity-related equation. On each point, we evaluate each of the RHS terms and get the minimum combination of the dominant mathematical terms, truly driving the RHS. By doing so, we can extract points sharing common local dynamics from different superclusters, which is beneficial in mechanically analyzing the evolution mechanism of the superclusters. Here, we apply the omnidirectional clustering method we previously developed to a low-speed jet noise. In order to better understand the significance of vortices, we conducted experiments prior to performing numerical simulations. The sound produced by placing a coaxial ring downstream of a circular jet is known as a ringtone. It is enhanced through a phase-matching feedback process involving the growth of vortex rings in the jet shell layer, their impingement on the ring, the upstream propagation of pressure waves, and the subsequent perturbation of the jet shell layer at the nozzle exit. This figure shows the test section in which a ring is placed coaxially downstream of a circular wind tunnel nozzle. A circular jet issues from the nozzle, which has an inner diameter of 30 mm. The ring has an inner diameter of 30 mm and a thickness of 5 mm. The impingement length LIM was varied from 20 to 40 mm, and flow velocities below 15 meters per second were considered in this study. The figure in the upper right shows the result of smoke visualization, in which the growth of disturbances and the formation of vortices along the outer edge of the jet can be observed. Depending on the impingement length, LIM, and the flow velocity, the acoustic spectra exhibit pronounced peaks originating from the behavior of these vortices. Here, we show the CFD results for an impingement length of 30 mm and a jet velocity of 10 m per second. In the first row, you can see the results from a fully compressible Navier-Stokes simulation using finite difference method, where we visualize the flow with Liutex omega I-surfaces. This lets us capture the vortex structures around the ring very clearly. In the second row, we extracted the points where the Liutex omega value is above 0.95. This gives a simplified point cloud view that shows how the vortices deform around the ring. In the third row, our hierarchical vortex clustering method using point clouds extracted by Liutex omega works nicely, producing locally connected discrete superclusters. Coupling of hierarchical clustering method for volumetric vertical regions with Liutex is proposed. Point clouds in vertical regions are extracted from an instantaneous flow field using a series of planes and are grouped between consecutive planes. Cross-sectional distributions of points are then stacked in a direction. Each group of extracted points is identifiable as an individual entity that is referred to as a P-cluster, with the letter P replaced by the terms proto, sub, super, and hyper according to the level of clustering. The present method is applied to transitional boundary layer flows on the flat plate and the ring tone. Linkage between vertical regions, its spatial distribution, and the time variation of the vertical regions in the computational domain are successfully extracted by the proposed method. Due to the realization of the individual identification of P-clusters with unique identification numbers, the algorithmic analysis of its dynamics and statistical properties is realized. Elements are clustered within each supercluster, which enables to extract subclusters having a common minimum combination of the dominant mathematical terms from different superclusters.